What about the Riemann hypothesis? The Riemann's hypothesis specifies that the so-called Riemann Zeta function has its zeros only at the negative even integers and complex numbers with real part 1/2. Many consider it to be the most important unsolved problem in pure mathematics. It is of great interest in number theory because it implies results about the distribution of prime numbers. It was proposed by Bernhard Riemann in 1859. The Millennium Prize problems are 7 mathematics conjectures chosen by the Clay Institute in 2000. Each prize amounts to $1 million. What about having your share with a $50,000 reward? Help to win the prize, you will get the money. You are a mathematician. First step. Check the proof. Second step. According to you, it is wrong. End of it. No winner. If it is right, third step. You can do something leading to the prize attribution. If so, you will get your share. There will be only one reward. Let us now start with the short sketch of our proof. The Dirichlet Eta function is an analytic continuation of the Riemann Zeta function. Let us consider the sum of the square of its real part and the square of its imaginary part. Let us note d0 the half value of the sum. The zeros of the continuation are the zeros of this otherwise strictly positive sum. If the second derivative versus the abscissa of the critical band is strictly positive on the left of the critical line, then no zero can exist there, nor on the right side, thanks to the functional equation. Let us note d2 this second derivative. One can extract a new expression. Let us call it R2. R2 is a function of a and b, respectively the real part and the imaginary part of the current coordinates. If the minimum value of R2 is -1 on the left side of the critical line, meaning for a in interval 0 to 1/2, then the Riemann hypothesis is true. Let us have a look to some numerical data with a varying from 0 to 1. The viewer can see the results within the critical band. Chaos and shambles are the rule on the right side of this chart where parameter a is greater than 1/2, while constraint reigns on the left side where the parameter is smaller than this precise value. Further numeric data shown also that R2 varies rapidly with small positive or negative values and large positive peaks. It happens that there is a relationship between the R2 peaks values and the minimal negative values of R2 on either side of the peaks. Higher peaks, lower values on either side. The condition is sufficient but not necessary. Failure is of no incidence if one can check the hypothesis in some other way, which is the case for small imaginary values. Our proof is only useful after the billions of already identified zeros, that is, the proof is essentially needed asymptotically. We prove that the asymptotic value of R2 is -1/2, which is here far away from the critical condition -1. More precisely, the closer the Riemann zeros, which is the case asymptotically, more close the -1/2 value as indicated by this chart where distance between zeros is on x-coordinate and R2 on y-coordinate. We prove also that the minimum value is -1, except for imaginary part of parameter a less than 4, which doesn't matter. In this chart, every blue point is some R2 representative. The points can hardly escape from the in green delimited zone and in no way are able to reach the critical -1 limit on the red line's intersection. Of course, numerical evidence is not sufficient. In order to go further and get the full scope of the proof, one needs to turn to another media. The viewer will find more on the subject at either of the following links. We wish you a pleasant reading. What about some comments underneath after that?